Hello, everyone, and welcome. My name is Liz Pimper, and I'll be your moderator for today's webinar, Bridge Deck Preservation Portal Part 1, sponsored by FHWA, Iowa DOT, and WJE. During the next hour, Dr. Mohamed ElBatanouny of WJE, Mr. James Nelson of Iowa DOT, and Mr. Raj Ailaney of FHWA will discuss the completed Phase 1 of this research aimed to develop a framework for a bridge deck preservation tool that can help engineers at state and local departments of transportation choose the optimum preservation action for a given bridge deck. This presentation is copyrighted by Wis Janney Elsner Associates. And now I will turn it over to Raj to get us started. Raj?
Thank you, Liz. Good day, everyone, and thank you for joining today's webinar on Bridge Deck Preservation Portal Project. My name is Raj Ailaney. I'm a senior bridge engineer with Federal Highway Administration, Office of Bridges and Structures in Washington, D.C. We all know bridge owners must employ cost-effective asset management strategies to maintain their bridge inventory in good and fair condition. Preservation actions, whether they're cyclic or condition-based, they extend the service life of bridges and bridge elements. Of the three major components of a bridge, decks are the most used component and therefore have significant impact on the quality of service and the public's perception of bridge condition. The objective of this project is to develop a deck preservation portal that provides deck maintenance matrices and decision trees for concrete, steel, and timber bridge decks. Today, we are presenting a proof of concept as first phase of this project. We hope that this tool, when developed, will provide optimized solutions for preserving bridge decks among states and local agencies. Today, I have with me Mr. James Nelson from Iowa Department of Transportation and Dr. Mohamed ElBatanouny with WJE. Mr. Nelson is the director of the Bridges and Structures Bureau at the Iowa Department of Transportation. He is also the chair of ASHRAE Technical Committee on Bridge Preservation T9. And Dr. ElBatanouny is with WJE, and he is the principal investigator for this project. With this, I'll request Jim to give a few remarks on this project. Jim?
Thank you, Raj, for the introduction. Good afternoon and good morning to those who are joining us west of the Central Time Zone. Thank you for taking the time for this webinar today. I know many people are focused on planning for continuity of operations and contingencies for the COVID-19 pandemic. I'm glad you can all join us for a bit to focus on our more typical work of maintaining bridges. As Raj said, my name is Jim Nelson. I work for the Bridges and Structures Bureau at the Iowa DOT. The state of Iowa has a significant number of bridges on the national inventory, just over 24,000 in fact. We have an extensive farm-to-market network used to move goods and commodities to the world market efficiently. Nearly 19,000 of our bridges are on low-volume secondary roads. On the primary system, consisting of interstate, U.S., and state highways, the Iowa DOT maintains just over 4,100 bridges. And we've made a significant effort to reduce the number of bridges classified as poor down to just 39 bridges, or less than 1% of our primary system bridges. Well, that's very promising news. There's also concern given the large number of bridges that were built in the 1960s and 70s. They're still part of our inventory. For the Iowa DOT, our average age of bridge replacement is now just over 62 years. For our primary system investment plan to be sustainable, we would need to be replacing about 65 bridges annually, which is more than what we're currently doing. In short, we have an aging inventory that will continue to put significant pressure on our resources to maintain our infrastructure. A good program of bridge preservation is necessary for us to maintain the inventory that we have, and as part of a three-pronged strategy the Iowa DOT Bridges and Structures Bureau is using. First, we are emphasizing system stewardship over capacity expansion in order to replace more bridges on our inventory. Second, for the new bridges we build, we are trying to increase the service life of these bridges by using service life best practices to increase the resilience of our structures. Finally, as I said before, we are using bridge preservation practices to drive up the average age of our bridges at the time of replacement. We need longer lasting bridges. Bridge preservation is not without its challenges. The climate of Iowa is quite demanding in terms of performance of bridges. We have a significant number of snowfall events, and as a result, apply both liquid de-icing and solid products, which are very aggressive agents leading to bridge deterioration. That deterioration typically occurs in a top-down fashion on many of our bridges, attacking our bridge decks and joints first. This bridge deck preservation portal that has been proposed is an investment in a decision-making tool for specific bridge projects with a framework that uses data-driven and a probabilistic approach to assist us or any bridge engineer in making good decisions on maintenance actions to preserve our bridge decks. I would now like to introduce Dr. Mohamed ElBatanouny with WJE, who is the principal investigator for this project. Dr. ElBatanouny specializes in the practice areas of structure evaluation, health monitoring, non-destructive evaluation, research, and testing. He will describe the proposed modules of the bridge deck preservation portal, decision-making framework, and the algorithms used to make bridge deck preservation recommendations to a user of the bridge deck preservation portal. Dr. ElBatanouny?
Thank you, Jim and Raj, and thank you all for taking the time today to attend this webinar. Again, my name is Mohamed ElBatanouny. I'm with WJE, Structural Materials Engineer in our Northbrook office. And today, I'll talk about the effort that we just completed during the phase 1 of the project Bridge Deck Preservation Portal. I would like to start by acknowledging the effort of the WJE project team, Paul Krause, John Lawler, Kate Hawkins, and Marwa Abdulrahman. I would also like to acknowledge the assistance of our sub-consultant, Hanson Professional Services, as they were helping us with finding out ways to move forward with this to make it a web-based tool. Kurt Bilobreski, Howard Gottschall, and Becca Wagner. And also I would like to acknowledge the review and the guidance of the Technical Advisory Committee, Jim Nelson, Raj Ailaney, Benjamin Foster, Chris Keegan, Travis Kinney, Ting Lu, and Tim Sherrill. So now to the framework of our project. So the objective of our Bridge Deck Preservation Portal Phase 1 project was to basically answer these 3 questions that I have here. So many state DOTs have been using bridge preservation strategies to extend the service life of their bridge decks. But the question always comes, what is the best maintenance action or preservation actions that I can choose in my scenario? This will depend on different factors, including the age and the pre-existing condition of your asset, your exposure conditions. Is it severe exposure or is it just mild exposure? And also how much money you would like to spend and how long you would like to keep that bridge deck in service. And in order to make these decisions, good information is needed. So the objective of the framework for the tools that we developed in this project is to supply cost, service life, and risk and uncertainty information so bridge owners can choose good bridge deck maintenance strategies. One thing to note here is that this project is a project-level tool. So basically, after you do your network-level analysis and you choose some of the bridge decks that you'd like to fix or preserve now, you can then use our tool that we developed here to choose the optimum maintenance action or maintenance action plan for your specific bridge deck. As I indicated, the phase 1 of the project is completed, and TAC is currently working on developing an RFP for the phase 2 of the effort, which will take the framework that we've developed here and make it into either a computer-based or a web-based portal for state DOTs and county engineers to access and use. In this presentation today, I will first discuss the theories and basically the framework that we developed. And then the second part of the presentation, I will give some examples to illustrate how this logic that we built can be used. So for our tools general framework is that the user will need to collect some information about their asset and basically input it for the tool to work. This will include physical description, exposure conditions, deck condition, and user preferences and constraints. Once the user have these inputs in, then we compiled, and I will explain this in detail later in the presentation, but we basically compiled a list of all the different maintenance activities that can be used based on the type of the bridge deck or the degradation condition. So for structural decks, if it's concrete, we focus on collecting maintenance actions for chloride-induced corrosion. If it's steel, we're also focusing on corrosion. If it is timber, we're focusing on decay. For wearing surfaces, the main deterioration we are targeting here is abrasion or skid resistance. So using the inputs, the portal have brains and logic to basically recommend some maintenance activities to the engineer. The engineer will still be able to add any maintenance activities, even if they are not recommended by the portal, in the analysis, or take out some of the maintenance activities that were recommended by the portal, but the engineer doesn't want to consider. And once you have the user inputs and the maintenance activities, then the portal has some algorithms to calculate some of the specifics about the analysis. And these are basically the service life extension estimate. So for each maintenance activity, there will be a calculation of how much service life that activity will extend your bridge with. And then this combined with deterioration modeling can give you a full picture of how long your bridge deck can remain in service using these different maintenance activities. And finally, we can do a life cycle cost analysis. The results from all these three algorithms is then compiled into an optimization module. And from here, the portal will develop some outputs for the engineer. These outputs will include list of maintenance activities that are ranked by life cycle costs. Agency costs are primarily or user costs. Service life extension, initial cost, and data variance as well. One thing to note is data variance will be an output because we are using a probabilistic model, and we are doing probabilistic analysis in this study, and I will explain this later on, which will basically start with a service life extension estimate, which is a probabilistic algorithm. So first, starting with the inputs, here I have some of the inputs that we need or the portal need to work. Starting with physical description, for example, the portal will need the year at which the bridge deck was constructed. And this will be mainly used in the DM or in the deterioration model module. We have other inputs here, which is the structure type, the surface area, and so on. Then we will also need some information regarding the deck condition. So, for example, we need the inspection or the NBI deck rating, and this will be used in selection of the maintenance actions and the service life extension estimates, and also in the deterioration model algorithm. Then we need information regarding the exposure conditions, which will basically be used in the service life extension estimate algorithm. And we also have user preferences and constraints. And you can notice that some of these inputs with asterisk are optional. So the portal will still work if these inputs were not put by the user. However, we recommend that as much information as we get will improve the results that the portal will output. So once you have the input, one of the main efforts that we completed during this project was basically compiling a database for all of the different maintenance action techniques that can be used for bridge decks. And again, we divided those per structure type, as I'm showing here. So for concrete decks or wearing surfaces, we have 5 maintenance actions that we collected. For asphalt wearing surfaces, we have 3 maintenance actions. For steel decks or timber decks, we have 4 for each. And for overlays, we have a total of 10 different maintenance actions that we included in the database that's also included as an appendix in the report. So for each of the maintenance action, we built what we call the maintenance profile. I'm showing here the example for placing a concrete overlay maintenance action. So Each action will include general description and general procedures for applying that maintenance action. We also collected unit cost information from the literature. This will basically be used in the life cycle cost analysis. One thing to note here is that cost information is very important because it's a big part of the decision-making process, and therefore we recommend that each state compiles their own cost information in a database and use it in this portal, because basically in the literature we found that there is a very large variance in the cost between different states depending on how much they use a certain maintenance activity. And then we also collected service life information, which we basically found for this one is that there is a range. So the literature will say if you apply a concrete overlay, that will give you between 15 and 30 years for the service life extension. And I will show later how we are using this information. And then we have some exclusion filters, and this is basically the logic that the portal will use to recommend or exclude maintenance activities based on the inputs of the user. And finally, we also included some thresholds for element level inspection data, and we got this mainly from the NCDOT 1436 report, which was completed by Dr. George Hearn from the University of Colorado Boulder. Here I'm showing example of exclusion filters. We have this for all of the different maintenance actions that we have for our portal. But as an example, for applying a penetrating sealer, if your NBI condition rating is 6 or 5, the portal will not recommend this action. And the user will still have the freedom, even if the portal doesn't recommend the action, the user will still be able to select that action for further analysis if they would like to. Same thing with the primary purpose of maintenance. If the user input that the primary purpose of maintenance is improve the ride quality, then applying penetrating sealer based on our engineering judgment won't help, and it will not be recommended to the user. But again, the user can still select that action if they would like to. Once you have your maintenance activities selected, then a big part of this will be to know what is the service life extension that you can get from each of the maintenance activities. As I indicated earlier, from the literature, we found that for each maintenance activities, there is a range. The assumption is if you apply, for example, again, a concrete overlay and your bridge deck condition is fair, is good, and you don't have a lot of chlorides that are logged into your bridge deck, and the traffic is not too high, and your de-icing practices are not very severe, then you can get the 30 years service life extension that we found in the literature as the upper bound. However, if your conditions are severe, you have high traffic, you have high chloride exposure, then probably your service life extension will be more towards the lower bound, which we found from the literature was 15 years. So what we developed here is an algorithm that based on your exposure condition and the pre-existing condition of your deck, you can basically take reduction factors and use them to reduce the upper bound of each of the service life maintenance actions, and then compare that to the lower bound so that your multiplication of the reduction factors times the upper bound is not less than the lower bound. One thing to note here is that these reduction factors we have that I have listed here will not be used with all the different maintenance activities. So, for example, for concrete, you may only use 4 reduction factors for concrete overlays. The reduction factors that we selected are one for traffic loads, which we call FADTT, one for chloride exposure. We have a reduction factor for the pre-existing condition or the NBI decreasing of the deck. We have a reduction factor for the freeze so cycles experienced by the deck. We have a reduction factor for the contractor experience. We have one for Schiffer index, which is mainly used for temper bridges. And we have a reduction factor for the average temperature and also the average relative humidity. And again, the way we do this is we multiply these reduction factors by the upper bound that we get from the literature review and compare it to the lower bound and take the maximum of the two. Here I'm showing a table example of different reduction factors that are used with different maintenance activities. So again, taking a penetrating sealer as an example, you have 3 reduction factors that you should consider: ADTP, the NBI condition rating, and the contractor experience. And the minimum and the maximum expected service life are listed here. Note that the minimum expected service life is assuming the condition or NBI rating of 7. Below 7, we actually reduce the minimum expected service life, but this is mentioned in detail in the report. Here I'm showing how we got the reduction factors. These are mainly based on engineering judgment, and they include probability distribution. So this is where our probabilistic analysis starts in the service life estimation, basically. And this is mainly because there is some inaccuracies in the service life estimates themselves and also in the reduction factors, which are again are mainly based on engineering judgment. So we wanted to include that in a probabilistic fashion. So taking an example of chloride exposure reduction factor, we have 3 categories for this: low exposure, medium, and high exposure. The low exposure is when you don't have chlorides, or you're using the ISAs for less than 5 days in a year. And in this case, the reduction factor is 1, meaning we don't reduce your service life estimate for your maintenance technique because your exposure is low. Once you go to medium, then we have 10% reduction, so a 0.9 reduction factor for the median, and 20% for the minimum reduction that you can see, because again, this is probabilistic, so we have a range. And if you have high exposure, then we reduce your upper bound by 10%, and then your median or average by 20%, and then your lower bound by 30%. So you use 0.7, 0.8, and 0.9. Here is a slide showing these different probability distribution in a graphical format. And as you can see, as your chloride exposure gets higher, the reduction factor is lower number. So we are expecting that your maintenance activity will have less life or less service life extension. Same with the pre-existing condition. As your NBI rating decreases from 8 to 5, you can also see a decrease in our service life extension estimate. So once you do that, now we want to understand how applying that maintenance activity will affect my bridge deck. And for this, we can use deterioration models. So the traditional way is that if I have a bridge deck that have a rate of deterioration similar or a deterioration curve similar to the one I'm showing here on the left in the black line. And then at about year 35, I apply a maintenance activity. This will cause an improvement in my NBI rating and cause a bump, basically, in my rating, and then my bridge will continue deteriorating with the same rate. So this is the traditional method. When we looked at this, we found that there is 2 drawbacks for doing it this way. So the first drawback is we don't know how much improvement in the NBI rating we'll get. What we found in the literature is when you apply a maintenance activity, you basically extend the service life of your bridge for a number of years. And then the second part is that we know that when you fix your bridge or when you put the overlay, you are effectively reducing the deterioration rate. So it doesn't make sense to use the same deterioration rate as the original line. So what we did for the portal is that we said, okay, if I have the same deterioration curve in the black curve here, and I know that I will apply my maintenance action at a time TI, and I know that my end of service life, if I do nothing, is TF, I can calculate the original rate of deterioration of my current bridge deck as the green line here. However, if I apply maintenance activity at this time I can extend my service life by, for example, 20 years, as I'm showing here, from 50 to 70 to time TF1. And in that case, I can calculate a new deterioration rate, which is I'm showing here in the yellow line. if I take the ratio between these two deterioration rates, the new deterioration rate after applying the maintenance activity and the old deterioration rate if I do nothing, and multiply it by the black line, I can calculate this new blue deterioration curve, which is the deterioration curve of my bridge after applying my maintenance activity. So by doing so, we can basically get the service life extension, and we can also back calculate an improvement in the NPI condition as I'm showing in this figure. And then we can use some of these parameters in the optimization and in the selection of the maintenance activities. Once you have this information, we can then do a life cycle cost analysis. And for this part, this is already well established. We looked at the literature and found that you can do the life cycle cost analysis using the agency costs. And sometimes people include the user costs, which is considered a good practice. And we recommend that it's being done. However, for this, what you do is generally you have a maintenance plan. So you apply maintenance activity at a certain time. Then after 20 years, for example, in the future, you apply another activity, and then you replace the bridge. And you're basically looking at a certain time frame. Typically 100 years is what we are assuming in our project. And what you do is that you calculate all these different maintenance activities and replacement activities. You calculate how much they are in the future, and then you translate all this to what we call the present value, so the present costs right now, and you can compare different maintenance activity profiles using this technique. And I will show this later on in the examples too. Again, as I mentioned, we are doing all this in a probabilistic fashion, and what we recommend to use to do this is a Monte Carlo simulation. And we're mainly following a probabilistic technique because we have uncertainties regarding to the remaining service life due to the inaccurate descriptions of exposure conditions and the assumption that we may have some compromised construction quality, and there is also some inaccuracies inherent in the deterioration model. So our main probabilistic analysis is conducted in the service life estimation algorithm, and then it goes on to the deterioration model and the life cycle cost analysis. We can have another level of complexity and another level of probabilistic analysis if we want to put the costs as also probability distribution. However, when we did the examples, which I will show later on by building a MATLAB code to do these analysis, we only considered that we have uncertainty in the service life estimate, and we took the cost as just a deterministic value. And finally, the portal can optimize all these results based on the objectives that the user need. And we define 3 objectives here: minimize the life cycle cost of the agency, minimize the life cycle cost of the user, and maximize the remaining service life. So the user can choose one of these objectives and do the optimization on, or we can combine these objectives using the linear weighted sum method and basically optimize each of them individually, and then sum this optimization into one function that I'm showing here, where the summation of the different weights that you get for each optimization function should be equal to 1. And again, I will show this in the examples. And also, finally, we developed basically a technique to make maintenance activity plans automated and optimized. So we know that in some cases, when preservation is considered for a bridge deck, usually you say, okay, I'm going to put penetrating sealer now, and then after 5 years, I will put an overlay, and maybe after another 20 years, I'll put another overlay. In this case, you're not only considering the immediate action, but you're actually considering a whole maintenance plan through the service life of your bridge deck. And there is a way to make this, which I'm showing it here, which is basically after the user inputs his input for the bridge deck, the portal can take this input and go through the filters and threshold module and choose some maintenance actions. So for maintenance activity plan 1, it will be action 1.1. For maintenance activity plan 2, it will be action 2.1, and so on. And then take these and put it in the service life extension and deterioration model algorithm, get new inputs, and go back to the filter and thresholds module and do actions 1.2, 2.2, and so on. So basically, we can make it so that the portal build maintenance activity plans and compare them and optimize based on whole activity plan rather than just the immediate preservation action. So now going to the examples. So early on in this project, when we met with the TAC, we basically all decided that it might be a good idea that after we develop the logic, that we run some examples to test this logic. And we got 3 bridges from North Carolina DOT, from Iowa DOT, and from Oregon DOT, and we did the analysis for all of them. In order to do so, we had to build a tool to do the analysis. So we built a MATLAB or completed a MATLAB code that can do the analysis that I described as an example and run all these example bridges and get the results, which I will show here. One thing to note is this is a preliminary tool. It's not complete, so there is some limitations of what we can do, but the service life extension and the iteration model and the life cycle cost algorithm are basically similar to what I showed in the previous slide. So for all the examples where we only considered a concrete bridge deck, and we selected 4 maintenance actions to be analyzed. So in doing so, we didn't have to build a whole maintenance selection algorithm because we already know what actions we want to consider. And we calculated the life cycle costs for agency costs only to keep it simple. And we considered 100 years for the life cycle cost analysis. There are 4 maintenance actions that we selected are a healer sealer, a hot mixed asphalt overlay with a waterproofing membrane, a concrete overlay or a PCC or a high-performance concrete overlay because they have similar characteristics, and a thick or a pre-mixed polymer concrete overlay. Here I'm showing the minimum service life extension based on your NBI rating and also the maximum service life extension. I'm showing some of the cost information that we collected from the literature and also the reduction factors that should be considered. One thing to note for a healer sealer, you have 4 reduction factors, traffic, pre-existing condition, free soak, contractor. However, for a thick polymer overlay, you only have 2 reduction factors, which are basically the pre-existing condition or the NDI rating of your bridge deck and the contractor experience. We ran the 3 examples, but for the sake of time in this presentation, I will only present onto the North Carolina and the Iowa DOT bridges. So for the North Carolina bridge, we got the inputs from InfoBridge, which is a website that FHWA have and have all the information that we needed, basically. You can also get this information from inspection reports. So for this bridge deck, the year constructed was 1979. It was built using concrete cast in place. We got the length and width information. And then we also got the location and the exposure conditions. So they used the icing salts for this bridge. The chloride exposure was medium. The free soak exposure was low. And we had the ADT and percent ADTT information to calculate the reduction factor for traffic loads. And we assumed that the contractor experience risk is low. So that means the contractor is experienced in all the method, and we don't need to put a reduction on the service life estimate due to inexperience of the contractor. And then we got the deterioration model, which is now available on InfoBridge, but at the time of this project, we got it from the LTBP portal. And this is a deterioration model for the bridge deck. We ran the example in our MATLAB program. And here's the results we got for the healer sealer and for the HMA with membrane. So the red line here is the deterioration curve, original deterioration curve of your bridge deck if you don't do anything. However, if you come at year 2019, which is the year we consider the maintenance activity, and you apply a healer sealer, you will get about 6 years of extension, which is that blue line here. You notice there's two purple lines around the blue line. These are the upper and lower bound, because again, this is a probabilistic analysis, so you get a range of the results. And these are basically the 10th percentile and the 90th percentile, and the blue line is average, or the 50th percentile. Same for the HMA with membrane, but you can notice that we got more service life extension. So instead of getting about 6 years, we're actually getting here closer to 9 years. For a concrete overlay or a thick polymer overlay, we did the same analysis. However, for this, you get a longer service life, because overlay gives you longer service life. So once you do this, then we can do the life cycle cost analysis. We assumed, again, 100 years, and for our life cycle cost analysis, we assumed that once the bridge deck reaches the end of its service life, it will be replaced. And then after 54 years, which is the new life of the bridge deck, which is assumed to be equal to the old life, to the life of the old deck, you will replace it again. So if you do nothing, after 14 years, you will reach the end of your service life, which we assume to be NBI rating of 4 in our case. So you will replace your bridge, and then 54 years, you will replace your bridge again, and then after 32 years, you will reach the 100 years, which is the analysis period, so you can calculate the salvage value and use this information to calculate the life cycle cost. If you put the overlay, instead of having to replace the bridge after 14 years, you extend that service life by 16 years, so you will have to replace it at 30 years. So you put an overlay, then after 30 years you replace. Then 54 years you replace again, assuming you don't do anything. And then after 16 years you reach the end of our analysis period, and you can calculate the salvage value and calculate the life cycle cost. And you can do that for all the different maintenance activities. So here I'm showing an example of the different variables or results you get for a healer sealer in this case. So do nothing is always there. It's always an option. It's default. And then the healer sealer results are shown here for the 10th and 50th and 90th percentile. For comparing all the different maintenance activities, we will choose the 50th percentile moving forward. But depending on how conservative you want to be, you can choose the 10th percentile. This would be the most conservative one. Or if you want to be less conservative, you can choose the 90th percentile. But the variables that we can, or the outputs that we get, are the undiscounted sum, the present value, which is one of the things we use for our optimization, the improved NBI condition, and this is a theoretical number, the remaining service life, which is the second factor we choose for the optimization that I will show later, service life extension years, and the initial cost. So here is one of the outputs that you will get from the portal, which is basically a very simple chart. If you just want to select a maintenance activity or the cheapest maintenance activities that can give you a certain number of years. So for example, if you only want 10 years out of your bridge deck, you can go to this chart and see that these three options, the HMA with overlay, the thick polymer concrete, and the concrete overlay can give you 10 years or more. And then if you want the cheapest option, you can choose the HMA with a membrane. If you only want 5 years, you can even go to the healer sealer and choose it, in this case, as your maintenance activity. So this chart can be used for quick selection of maintenance actions that you can apply now and give you a certain number of years for service life extension. But you can also look at the different variables and the different techniques and then do the optimization using the life cycle cost and the remaining service life. So in this case, if I'm looking at the present value, the cheapest option in terms of life cycle cost is the thick polymer overlay. It's not the cheapest to put now because the initial cost of it is actually higher than the other two. Here, the healer sealer and the HMA. However, for a life cycle cost, this will be the lowest cost based on the inputs we have. And then the concrete overlay will give you the most service life. Will give you 31.2 years on the 50th percentile. So if I do the optimization for the present value, you can notice that the thick polymer overlay is 1, which is the optimum solution. If I do it for the remaining service life, life, you will notice that the concrete overlay is 1, which is the optimum solution if I'm looking for maximum service life extension. I can combine the two, which we did in this table here. So if I give them equal weight factors, so each of them gets 50%, then the optimum solution based on the inputs that we have here is the thick polymer overlay. If I have a higher priority to the present value, so 75% to the present value and 25% for the remaining service life, then again, the thick polymer concrete overlay is the optimum solution based on our inputs. And if I have a higher priority to the remaining service life, then my optimum solution will be the concrete overlay. So moving to the Iowa DOT bridge, this is actually a newer bridge. It was built into 2010. Again, concrete cast in place, and we have the length and width information. The ride exposure in Iowa is high, and the free source cycling is high. And this bridge had a high number of ADT and present ADTT. And we assumed in this case that the contractor experience is variable. So what we said is that contractors in Iowa are experienced in healer sealers and concrete overlay, so these have low risk. However, the HMA or the hot mix asphalt with membrane or thick polymer concrete overlay have a high contractor risk. And again, all this information for the inputs you can get from the InfoBridge website. And then we got the iteration model, which I'm showing here. So again, we ran the analysis, but this time we wanted to look what will happen if I am choosing maintenance activities for the same bridge, but it had different NBI ratings. So if I am applying a concrete overlay at the current NBI rating, I'm looking at about 25 years of service life extension. If I apply it an NBI rating of 8, that reduces a little bit, so instead of 25 years, I'm getting like 22 or 23 years here. If I apply it at NBI 7, I'm getting even less service life extension. And this one you're looking at maybe 19 or 18 years. If I apply it an NBI 6, the service life extension is less and less. And if I apply it an NBI 5, you're getting less than 15 years of service life extension. And this is mainly because that pre-existing condition factor that we have in our service life extension estimate. As your NBI rating decreases, your reduction factor increases, so that makes your service life lower. So again, I'm showing the simpler chart, which includes information for the initial cost and service life extension. And you can see here the information for a concrete overlay or thick polymer or HMA, which is yellow, or the healer sealer. And again, as you apply this at a lower NBI rating, you get lower service life extension. So I'm showing here at NBI 7, maybe the healer sealer is a little bit over 5 years. Then at NBI 6, the healer sealers actually give you less than 5 years. And at NBI 5, it's about 4 years. So you get lower service life extension. This is true for all of the different maintenance activities. Then we wanted to check if the recommendation from the portal will change based, again, on when you apply your maintenance activity with regards to the NBI rating. So for the present value, the healer sealer was going to be the recommended option based on our inputs for NBI rating of 8.7 or NBI rating of 8. Once you go down to NBI rating of 7, 6, and 5, the thick polymer overlay will have the lowest life cycle cost based on our inputs. For the remaining service life, you can see it here that the concrete overlay will almost give you the maximum remaining service life or service life extension, and this is due to the inputs that we have. If you change the inputs based on your condition, again, if your bridge deck, these results may change as well. And finally, if you want to do the optimization based on different weight factors, so equal weight factors or priority to present value or priority to remaining service life. You can see that with the changing the NBI rating, the recommendation of the portal will change. Again, that's based on the inputs that we have in this case, with the healer sealer being one of the best options when you have a high NBI rating, but once your NBI rating becomes lower, then the overlays become a better option in this case. So in summary, in this project, we developed a framework for a web-based bridge deck preservation portal that includes the cost, service life, and risk and uncertainty information. WJE developed the following tools as part of the portal. The first one is a database for the different maintenance actions that includes the general procedures, the cost information, the service life extension information, and some filtering techniques for recommendation of maintenance actions. We built a service life estimation algorithm for the different maintenance actions. This can be used with the deterioration model, such as InfoBridge, to estimate the life cycle extension. However, our portal will have enough flexibility, so if the user doesn't like what we recommend in terms of the service life extension, they can have their own input. So instead of using 20 years for concrete overlays, if they want to use 30 or 35, they can. The user will have complete freedom to have this input. And they can also use their in-house deterioration models if they have them. If you don't have your in-house deterioration models, we recommend that the information InfoBridge be used. And finally, we put all this in a probabilistic framework to account for the uncertainties in the inputs and subsequently the remaining service life and life cycle cost. WJE developed a MATLAB-based tool, preliminary tool, to conduct the examples. We can keep developing this tool and use it in the phase 2 or in future projects to compare with the web-based tool if this is the direction we're going. So the main outcome from this, in my opinion, is that this proposed framework that we developed here is a project-level tool that can be used to optimize the selection of maintenance actions and plans. And this can lead to optimized management of funds and enhancing the life cycle cost of the assets. The tool can also be used as a data depository in the future, which can be used to further refine the portal assumptions and ultimately improve the accuracy of the results. So what's next? As I mentioned earlier, TAC is currently developing an RFP for the phase 2 effort, which will take the framework that we developed here and make it into a computer or a web-based tool. Maintenance action costs are of extreme importance and have significant effect on the results. We either assume to conduct a study to collect this cost information for each state, or each state can use values from their bidding items for this case. The service life estimation algorithm is based on literature search and engineering judgment, particularly the reduction factors. We recommend that a parametric study of the different scenarios be completed because this can refine any of the factors. However, again, as I mentioned earlier, the user will have the complete freedom to input what they estimate for service life extension for the different maintenance actions if they choose so. Delayed maintenance and optimization of maintenance may be of interest, and this could be further developed if needed. And finally, the developed framework for bridge decks in this case is scalable and could be adopted for other bridge elements, including superstructure and substructure elements. At the end, I would like again to thank you all who attended this webinar, especially during these difficult times, and I hope that all of you stay safe and healthy. Any questions?
Thank you, Mohamed. All right, as a reminder, if you have a question, please type it into the Q&A box and hit submit. We have lots of good questions, and we'll take as many as we have time for today. But if we don't get to your question during today's call, Raj or Jim or Mohamed will follow up with you afterward. So let's go ahead and take our first question. Bridge management systems used by various owner agencies also conduct project-level analysis to identify multiple alternatives for each bridge and apply the alternatives in a network-level analysis to determine the most effective combination of projects subject to budget and constraints. How is this portal different?
Yeah, Liz, I can respond to this question, and I think Dr. ElBatanouny clearly mentioned in his slides that this portal is solely a project-level analysis tool, and its focus is only on bridge decks, unlike the bridge management systems, which also perform network-level analysis and include all bridge components or elements. This tool offers additional functionality beyond the common BMS project-level analysis function. One use case may be to take the project recommendations from an existing BMS and substantiate the need for the project, or refine the project scope and timing of the deck work based on additional site-specific information. As we mentioned, in the report we have about, in the Appendix B, we have about 27 different maintenance action types. And the user has the option to use supplemental information, such as chloride content of the rebar depth, half-cell potential values, exposure conditions such as primary chloride sources, and user preferences or constraints such as primary purpose of maintenance. So user has a lot of flexibility here in terms of selecting the additional maintenance actions or remove from the portal recommended actions from further analysis. So as we mentioned that, once the maintenance actions are determined, they can be optimized through those three built-in algorithms, what he already explained. So I think, as I mentioned, this is mostly a project-level analysis tool, but it gives you more options since we have quite a bit of input in there, user input.
Okay, thank you. The next question is, can this bridge deck preservation portal be used for railroad bridges?
Yeah, Liz, I can take that one. So the portal was developed with reference material and models from highway bridges, and so if you were using it for a railroad bridge, you'd have to keep that in mind. It doesn't mean that the portal wouldn't have utility potentially for railroad bridges, especially if an owner was able to, upload their own in-house deterioration models or other data. So that's how I would answer that question.
All right, the next question. How are the reduction factors calculated or determined?
Yeah, I can take this one. So the reduction factors were determined based on our literature search and also engineering judgment on what reduction factors should be used for the different overlay options. So if I go back to the slide with the different reduction factors, which is here. So you can notice that not all the reduction factors are used for all the maintenance actions. Again, for example, a concrete overlay, we are only considering reduction factors related to chloride exposure, existing NBI rating condition, and contractor experience. However, if you look at an asphalt overlay, then all of a sudden we are now considering the ADTT or the traffic loads on your bridge deck in addition, or on your overlay in this case, in addition to, again, the chloride, the NBI rating, and the contractor experience. The value that we use for the reduction itself is purely engineering judgment. We basically chose these values based on our judgment and experience. And this is why we recommend that a further study, a parametric study, be conducted to actually fine-tune all these values. This is an initial recommendation for the framework that we built and to run the analysis. We did for the best of our ability at this point, but moving forward, this should be refined, and we highly recommend that this be refined if it's going to be widely used. The other thing is, again, we left some freedom to the users to choose their own service life extension. So if they know for certain techniques based on certain type of exposure in their state, that if you put an overlay, you get 15 years or 16 years or whatever. They can just use that too. So I hope I answered this question, and another question too that was asking about the concrete. So we don't use traffic for concrete overlays. We don't reduce the life based on the traffic exposure for concrete overlays, because the assumption that concrete overlays doesn't wear as much as like asphalt under high traffic loads, and we also don't break if you do your partial depth repairs well enough before you place your overlay. The assumption is concrete overlays will not break due to high traffic loads, or will not crack to high traffic loads, due to high traffic loads.
All right, our next question. Can you examine a series of action over life of a structure to determine the best combination of preservation or life cycle plans for a deck?
I can take this one too, and this is a really good question, and this is actually the intent. So the intent of this is you don't only test one action similar to what we did in the examples. We did that in the examples because the examples were mainly done to prove the logic, to prove that what we propose here will work. However, for actual bridge deck, we understand that you will have a maintenance activity plan, and at its current condition, we can add that. That can be easily done. If you look at the report, this is what we actually say in Chapter 3, which is the chapter that explains the framework. We basically say that we highly recommend that when you do this, you do it for your whole maintenance activity plan. If you have more than one plan and you want to compare them, you can do that. You can say, I'll do a sealer, overlay, an overlay, or I'll do a sealer, and then an overlay, and then you can compare all these different plans and choose and make the portal complete the analysis and recommend best options in your case. That's a really good question. Thank you.
Okay. Well, let me know if this was already answered by a previous answer to a question, but one question we have here says, why does ETT factor into concrete overlays?
So yeah, this one I answered. So ADTT does not factor for concrete overlays. And again, basically our assumption is even under high traffic loads, if you do your partial depth repairs before you apply your concrete overlay, that concrete overlay won't crack or deteriorate as fast as like an asphalt overlay or a thin polymer overlay or a penetrating sealer. So this was our engineering judgment in this case.
Okay, 2 quick questions. Can you save agency-specific settings or assumptions? And can you combine preservation actions in different years?
So based on the discussions we had with TAC, and this will be part of the phase 2 effort, I think TAC is moving towards having each of the states has the ability to save their own inputs, so they don't have to put inputs every time they try to run a model. So I think this is the intent, but again, this will be part of phase 2, not phase 1. For phase 1, what we developed here, the example MATLAB code that we have, it's very simple.
Okay, we're getting lots of questions about whether the presentation will be made available as a PDF after today's webinar, and the answer is yes, it will be available. Okay, next question. How is the end of service life extension defined?
So for this one, the assumption in this case is that once your deterioration curve reach an NBI rating of 4, then this is the end of your service life because this is more rehab and big repairs, not preservation or maintenance anymore. However, one thing I want to note here, and this is a good question because moving forward, a lot of the states and FHWA is implementing more the element level condition assessment. This portal now in its current state, we are using mostly the general NBI ratings because these are the ratings that we have deterioration models for. Moving forward, however, after maybe a number of years where we start building enough element level inspection data that we can start doing deterioration curves based on the element level data, then in this case, we can start defining end of service life based on the element level. But for now, it's based on the NBI rating, and the assumption is once your bridge deck reach an NBI rating of 4, then you should consider more aggressive actions, so partial and full depth repairs and so on.
Okay, we have time for one more question. During the research, was it found that any treatment options are obsolete? For example, treatment A always costs more and is less effective than treatment B.
So the quick answer is no, just because we didn't run enough models to get that. However, I want to add something here, is that it's all based on the inputs and based on the assumptions. What we noticed in the literature is that some states use preservation techniques that are not used in other states because other states they don't work or they didn't work for them when they applied them a long time ago, so they stopped using them and they never use them. But other states are using them all the time and they work well for their case. So that would be state specific, and I suspect that in some cases, yes, some maintenance techniques might give you better answer or might have a lower life cycle cost than others, and that could be based on your inputs for your state. That could be always true for a couple or 3 of the maintenance actions. But what will drive it in this case, in my opinion, will be the initial cost, because it might be more expensive to do what's best for the life cycle cost analysis. So you might want to choose a cheaper initial cost because there is not enough money to do the expensive ones that will give you a longer life. So I think the answer is no, and it will depend.
Okay, that is all the time we have for questions today. As a reminder, if we didn't get to your question, someone will follow up with you afterward. We'd like to thank you all for joining us, and we hope it's been educational. And I'd also like to extend a big thank you to Raj Ailaney and to Jim Nelson for partnering with us today on this webinar and also on this research project. As a reminder, you will receive an email with a link to an on-demand version of this webinar, which you can use to rewatch the presentation at your convenience or pass along to any colleagues who weren't able to join us today. And using that link, you can also access related resources, including a PDF copy of the slides that we'll add here in the next couple minutes. If you have any questions, please don't hesitate to reach out to any of today's presenters or to me, Liz Pimper at lpimper@wje.com. And again, thank you for your time. Stay safe, and we hope you have a great rest of the day.